So before we can handle doing calculus with logarithmic functions, we want to first of all review our properties of logs and go over some important properties about logarithmic and exponential functions. And what we see here is a list of important rules that we need to know from algebra, right? Starting with, like, if you have, and here I'm using ln. By the way, ln was logarithm to which base? Base e, right? So that's called the natural logarithm, base e. As a matter of fact, today we're going to have a better understanding about why we're using base e more than anything else. You know, why are we not using like base 10? Numbers are usually base 10, right? When you write, 735, that's a number in base 10. Why are we all of a sudden using logarithmic functions in a base different than 10? And what was e, by the way? E was just a number, right? It's like 2.718, similar to pi being 3.14. It's such a commonly used number that mathematicians gave it a special name. It's also a non-repeating decimal. So again, that's another reason perhaps it has a special name, E, after the mathematician, I think, who coiled this name, this letter, I think was mathematician with the name of Euler. So here we have property number 1. If you have ln of a plus b, you can write it as a product, right? ln of a times b. If you have difference of two logarithms, you can write that as ln of a over b as a quotient. Property number 3, if you have ln of a to a power, you can bring the power down, right? And also these numbers 4 and 5 get to be forgotten the most, I think. Let's take a look at them. If you have e to the ln function, e to the ln x, what's happening? They're canceling each other. Why is that? This is kind of similar to saying the square root of x to the second power is equal to x. Basically, the square root of x and squaring function, they cancel each other. Why? They're inverse functions of each other. If you apply one right after the other, you get back what you started with. Same thing with the exponential and log functions. If you apply e to a power right after you apply ln of something, they undo each other. They're inverse functions of each other, and you get x. Now, because they're inverse functions of each other, we have this graph. Do you remember from college algebra, if two functions are inverses of each other, what kind of a property do their graphs exhibit? If you know one of the functions, the other one will be symmetrical with respect to which line? With respect to the line y equals x. Remember something like this? So if this is the graph of y equals e to the x, if this is the graph of y equals e to the x, ln x will be symmetrical across the line y equals x. This is the line y equals x. So this is the graph of y equals ln x, basically. So they're inverses of each other, and therefore property number 4 works. They cancel each other. Property number 5 talks about what do you do if you're trying to get rid of a logarithm. How can you rewrite something in exponential form? So if you have log base a of x equals to y, how do you write it in exponential form? Does everybody remember that? I usually use these little arrows. Then you have a to the y is equal to x. And property number 6, change of base formula. Does anyone remember that one? Change of base formula. So say you have log base a of b. What is the base in that case? Log base a of b. The base is a. Now say that I want to convert this to base 10. So how can I write it with base 10? I can say this is the same as log of b over log of a. What is the base there? 10. If we don't write any base, it's understood to be base 10, right? So what if I want to convert it to a natural log, base e? So you take the same thing, log base a of b, you can write it as ln b over ln a. Now we convert it to base e. So you can convert it to any base you like, but the most commonly used bases are log and ln. Therefore, we convert them. That's why this property is only mentioning those two. So from base a, we can switch to base 10 or base e very easily by just writing it as a quotient. Now, we're going to do some examples today. And some of these are on your handout. Did everybody see it on the problem from the handout? Okay. So these are your typical examples that you would do in a typical college algebra class. And this is how I usually introduce logarithms in college algebra to a problem like this. So here we have $2,500 that we'll invest. We want it to grow into $4,750 at 7% compounded continuously interest. The question is, how long would this take? And I'll remind you of the formula that you might have seen in college algebra. It goes like this. Accumulated value equals the principal times e to the RT. And some people remember like A equals PERT, P times e to the RT. Maybe you remember it. P is your principal, R is the interest rate, compounded continuously, and T is the time in years. So the question is, how long will it take? So what is the unknown here? The unknown is T, right? So they want to know what is the time that it will take for principal of $2,500 at 7% interest, R is 0.07, to grow into what amount? $4,750. So I put the $4,750 on the left-hand side because that's the accumulated value. So take a look at this equation. It's very unusual. Where is the unknown in this equation? In the exponent. See, if you had something like this, if you had like x to the third power equals to 27, or let's say, make it any number you like, let's say 27. How do you solve for x in that equation? You apply what to both sides? The cube root, because cube root is the inverse function of x cubed. So if you want to undo the x cubed, you've got to apply the cube root to get x. But what is the inverse function of an exponential function? The logarithmic function. So if you want to get rid of an exponential meaning the unknown appears in the exponent, like t is in the exponent, you got to somehow need to use the logarithmic function to solve a problem like this. Now the first step is to isolate your exponential. So let's divide both sides by 2,500. So you go ahead and do 4,750 divided by 2,500 equals e to the 0.07t. And what did you get as a decimal? 1.9 equals e to the 0.07t. And to solve for t, what should I be doing? Apply ln to both sides. Again, you need to apply the inverse function to bring that t out of there. So apply ln to both sides. So I will take ln, or natural log of the left-hand side. That should be equal to the ln of the right-hand side. Now, ln of 1.9, we can easily get it on the calculator. 0.64 roughly. Now, on the right-hand side, we can simplify. Okay, what is ln e to the 0.07 in simplified form? Look at property number 3. ln a to the r is r ln a, right? So in this case, it's going to be 0.07 times, so bring the power down. And what do we know about ln e? ln e is the same as log base e of e. And anytime the base is equal to that number, that will be 1. So ln e is 1. It's a good one to know by heart, so you don't even have to use a calculator for that one. So the answer is t equals 0.64 divided by 0.07. So t equals 0.64 divided by 0.07. And let's see what that is. Roughly 9.1, so a little bit more than 9 years is what's needed for this investment to go to 4,750, about 9.14 years. Okay, could you do the next one, please? At what interest rate would $10,000 double in value in 12 years? I'll give you a minute to work on that one. So the accumulated value for this question is double the amount of what was invested, so it's going to be $20,000. That equals the principal, which is 10,000, times e to the RT. We don't know the interest rate, but we know the time is 12 years, right? So we divide both sides by 10,000. We get 2 is equal to e to the 12r. So what do I do at this point? Apply ln to both sides, because we really need the logarithmic functions when you're solving an equation with an unknown in the exponent. There's no other way to solve it. But you can use different log functions with different bases, but you need some sort of a log function to any base that you like to use. You could also use base 10 if you like. I prefer to use the natural log base. It really doesn't make a very big difference either way. So ln2 equals ln of the right-hand side. Of course, on the right-hand side, 12r comes down, and ln e is 1. So now r equals ln 2 divided by 12. And what you guys are getting for your interest rate here? Roughly 5.8%. So either rather to 6% or to the nearest tenth, 5.8%. All right, a little bit more reviewing. Of our logarithmic functions. This is question number 2 from that handout you got today. Yeah, you can just see later, and it's going to be very similar to parts A and B. So for question number 2, the question is, how can we solve the following without using a calculator? For example, log of 1,000. Any thoughts? You can set up an equation for it, right? So for log of 1,000, you could say, okay, this is equal to x. We don't know what it is. The hidden base here is 10, right? If they don't give you a base, that's base 10. And then you can write this in exponential form. What is it in exponential form? 10 to the x is equal to 1,000. From here, what can you tell me about x? Since 1,000 is 10 to which power? 10 to the 3, right? So x should be 3. Basically, you can think of log of 1,000 like this. That's log base 10 of 1,000. To what power should I raise 10 to get 1,000? And that power is 3, so that's what log of 1,000 represents. The power you need to raise the base to get that value. But I have another way to do this question. This is normally how I would do it. Okay, log of 1,000, I would write it like this. Log of 10 to the 3rd. And the base is 10, right? Now bring the 3 down. And what do we know about log base 10 of 10? It's equal to 1. So the answer is 3 once again. I want you to remember something here. Logarithmic function is a function that goes very slowly. For example, look at it. Log of 1,000 is only 3, a very small number, right? Log of a million, what will that be? Log of a million will be like 6, right? A million is 10 to the 6th power, log of a million. So it's going very slowly. At a million, the y value is only 6. So sometimes logarithmic functions are used when you're doing graphing, and the numbers at hand are like really, really large numbers, or sometimes you can use inverse log if the numbers are really, really small numbers. When you take the log of those numbers, you can get a much more meaningful graph. Those of you taking physics or chemistry, you can do some labs. You might do some of your graphs saying log of a variable against another variable, because then the graph looks so much nicer because you don't have to have these huge numbers. You've made the numbers much smaller. Like in statistics, we look at GDPs of different countries. Around the world, some countries have a GDP of $400 a year. That's like average income of citizens. Some countries have GDP of like 40,000 a year. That's like United States. To try to put them all on the same graph and trying to make some sense out of it, it was much more meaningful if we converted everything into logarithms. So if you take log of 400 and log of 40,000, then there's a much better scale that you can use, and you can show all these changes much easier on the graph. So that's another good application of logarithms. Okay, how about part B, ln of e cubed? How do we simplify that one? This one should be pretty easy. ln means base e, right? Log base e. So this is just like part A then, right? How would you rewrite this? 3 times ln e, right? With the property of logs, you can bring the power down, right? And ln e is 1 because it's log base e of e, so the answer is 3. How about part C, log base 4 of 16? I can rewrite that as log base 4 of 16 is the same as 4 squared, right? So the answer will be 2, because this is 2 times, bring the power down, 2 times log base 4 of 4. So that's 2 times 1, or 2. How could I do the same question on the calculator? Log base 4 of 16. There is no log base 4 key in my calculator, right? So what should I do? I should convert it to another base, say base 10. How would you write the same question with base 10 so I can check it on the calculator? Exactly, log 16 over log 4. So would you do that on the calculator, please? What do we get for log 16 over log 4? Make sure you close your parentheses after the 16. Did we get 2 once again? We should. We should be able to get 2 on the calculator also. Let's see, did I have another part there? A, B, C, and D. Log base 9 of 3. I won't even write that one down. Now you tell me, do it on your head, in your head. Log base 9, okay, maybe, I was thinking log base 3 of 9. This one, maybe we should still write it down. Okay. Log base 9 of 3. You can still do it in your head. If you think about it, this represents what power should I raise the 9 to get a 3? What, 1/2, so the answer will be 1/2. But if you want to do it the longer way, you can say, okay, this is equal to x, right? And then write an exponential form. 9 to the x is equal to 3. Okay, if I'm going to set the two sides equal, I want the same base. 9 is 3 to the 2nd power, or 3 to the 2x. So now I set the powers equal to, because the bases are the same. So 1 is equal to 2x, so what is x? 1/2. Again, if you can think it in your head, it's a lot easier. Sometimes if the numbers are messy, you cannot do it in your head, obviously. You have to set up an equation. But the ones that I had in this question, number 2, most of them were set up simply that they could be done without doing it on a piece of paper or on the calculator. Now, question 3 that I had for you is asked you to do these things on the calculator, just to make sure you know how to use these keys like e cubed. You can either do second ln for that. Second ln is e to the x. That probably would be the easiest way to do it. Do a second ln and to the 3rd power, and what are you getting? E cubed is 20.09, let's say, 20.09. Log of 25, again, there's just a log key in the calculator, no problems there. This one you would convert to base 10. And this one, there's already an ln key on the calculator, like part D, ln of 23. There is a logarithm base e key on the calculator, so this one is 3.14 roughly. And we've already done something like this, so I know you can finish that one or this one, part B. Again, that's just a simple calculator function. Log 25 is 1.44 roughly. Okay, and number 4 has to do with solving exponential equations. We've already done some things like that. When we're doing question number 1, we're solving exponential equations. So I'm going to basically let you guys do that one later. But in every one of those, you're going to need to apply ln to both sides. Although if you can get them on the same base, like base 2 on the left and 2 to a power on the right, you can probably do it even without a logarithm. But let's do something like 4f right now, 4f. Solving a logarithmic equation. Let's see, where do I have that one? Okay, one moment. Okay, let me get a new slide for that one. Okay, so for number 4f, say that you have, where did that come from? say we have log of x minus 3 is equal to 2. And while I'm at it, I will also write g on the board. Ln x is equal to 3. How do you solve these equations? Starting with 4f. Now, we need to get rid of the logarithm. In the past, number 1, for example, we applied ln to both sides to bring a variable down, right, to get it out of the exponential exponent. In this case, you have a log function. X is hidden under a log function. How do you get rid of the log function? Write it as an exponential this time, right? So the hidden base here is 10. So how will you write it as an exponential? 10 to the power of 2 is equal to x minus 3. Well, 10 to the 2 is 100 is equal to x minus 3. So what is x? 103. We add 3 to both sides. How about 4g? That's really one step. Write it in exponential form. If you know ln x is 3, what is x? What is the hidden base here? The hidden base is e. So we're going to write it as e to the third power is equal to x. And that's the answer. E to the third is the number. You can get it on the calculator. That is the answer there. What if you're solving something like I, 4i? Log base 2 of x plus log base 2 of x minus 6 is equal to 4. Once again, we want to get rid of the logarithm, but that property that allows you to go from logarithmic to exponential, it only works if you have only one logarithmic expression. But now we have 2. Is there a way to combine them and write it as a single log? Yes. How do we do it? Hold on, let me hear from another. Write it as log base 2 of the product of x times x minus 6. This was one of the first rules that we looked at earlier today, right? Log of a plus log of b is log of a times b, right? Okay, now we're ready to put in the exponential format. And how are we going to do that? 2 to the power of 4 is equal to what? X times x minus 6, which I'm going to write as x squared minus 6x. So it looks like we're getting 2 to the 4, 16. Can we factor this? Let's try it. Let's see, 16 is 2 times 8. Make the 8 negative and 2 positive, right? So the product is negative 16 and the middle term is negative 8x plus 2x, which is negative 6x. So it looks like we're getting two answers. X is equal to 8 and x is equal to negative 2. But anytime you solve a logarithmic equation, you got to be very, very careful. Sometimes you end up with these extraneous solutions that look like a solution, but it's really fake. It's not really a solution. And the only way to know for sure is to do a quick check. When I say a quick check, take the number and plug it back into the original equation. Make sure that you don't end up with a log of a negative number. Because you remember the graph of the ln function or the graph of a log function in general, something like this. It's not defined for negative x values, okay? So in this case, if you have x equals negative 2, plug it back in. Is it going to work? No, you have log base 2 of negative 2. It's not going to work. We have to reject that solution. We can only accept the positive 8 solution. Yes, because one of the properties, let's go back to see which property that was. It was this property right here, number 5. If you have log base a of x equals y, you can write it as a to the y equals to x. So we use that property. Because at negative 2, if you put it back to check, you end up with log of a negative 2. And if you put on the calculator, you'll see it's an error. It's not defined at a negative value. It's not in the domain of the logarithmic function. Okay. All right, how about number 5, a and b? I want to give you a few moments to think about these. We're going to use these properties quite a lot, so I hope you guys remembered, or by checking with the rules we learned today, you'll be able to do these. So the first one looks like ln of a over b, and there the rule was do ln a minus ln b, so the ln of the top minus ln of the bottom. And then the product portion can be written as like ln a plus ln b, right? So you can expand this one further as saying ln of x to the 6 plus ln of, I don't even need parentheses, y to the 4 minus ln of z to the 8. And you know what? Once you've done enough examples, you don't even need that intermediate step that I put down. Once you see the product on the top, you're going to write it as ln x to the 6 plus ln y to the 4. And you see the quotient, you say minus ln z to the 8. But there is one more thing I can do here. Any thoughts? Bring the powers down, and you can simplify it. This will be helpful today because we're going to differentiate logarithmic functions today. But instead of differentiating this, if you can break it down like the one we're doing right now, it's going to be so much easier to differentiate the function piece by piece. So you have 6 ln x plus 4 ln y minus 8 ln z. And for the second one, we're going to do the exact opposite. First, get rid of those coefficients. How do we do that? Put it as an exponent, so it's going to be x plus 1 to the 3rd minus 2x plus 1 to the 4th plus log base 2 of 3x minus 1 to the 5th. And I want a single logarithm now. That's going to be log base 2. What should I have on the top? The ones with positives, right? So x plus 1 cubed, and also 3x minus 1 to the 5. And what should I have on the bottom? 2x plus 1 to the 4th. So we wrote it as a single logarithm. Complete opposite process. Okay. So with that review, now we're getting ready to start the actual new material for today, which happens to be doing calculus with the exponential and logarithmic functions. We're going to begin with the exponential function and take a look at the derivative of the exponential function. Okay. Like I told you earlier, the derivatives of exponential functions and logarithmic functions are actually very, very simple. You would never think that something that looks so complicated, like e to the x, would end up with something so simple. But here is the derivative of the exponential function. And in a little bit, I'll try to give you the proof as to why this is true. But the rule says if you have the derivative of e to the x, it's hard to believe it, but the derivative will be exactly the same, e to the x. So it says the derivative of the exponential function to the base e is exactly the same as itself, e to the x. So at any given moment, the slope is going to be equal to its y coordinate, basically. Now, there is a slight variation if you have a different base, say base a, anything but e. So if you have a to the x, then the rule becomes a to the x times ln of the base, ln a. Now, do you see why the first one was so easy? Because if the base is e, what would this portion be if the base is e? ln e, and ln e is 1, right? So basically it turns out to be just a 1. So this is the reason why I think that they're calling this base e the natural base. Basically, it's the base that makes calculations the easiest. It's the base that has what the derivative of the e to the x function is exactly e to the x with no extra baggage, no extra coefficients there like ln a or ln of any other number. It's just the base that makes calculus the easiest. This is why we call it the natural base. So basically, what if you have you have to use a chain rule. Say you have the derivative of e to the u, where u is a function of x. Then just like before, First, you apply the regular derivative of e to the u is e to the u, but then you multiply it with du dx, the derivative of the inside function. Here, the inside function would be whatever your u is. And I'll do examples to that in just a moment. So if it's just e to the x, you know, the only other function I can think of that has its own derivative is which function? Anything? Even if derivative of 5 is 0, right? Derivative of 5 is not itself, but I can think of one more function. Or derivative of 0 is 0, right? That's the only other function that has its own derivative, or if you could consider y equals 0 to be the constant function of 0 or something. But so in that regard, it's really the easiest function to differentiate e to the x. Now, what do you do with something like e to the x squared plus 1? How do you differentiate something like this? It should be very easy applying this rule right here. Your u is x squared plus 1, right? So what will be the derivative? E to the same power, right, times the derivative of the power, which is 2x. Of course, you could write it like this, 2x times e to the x squared plus 1. How about this one, the derivative of e to the 2x? This is also of the form e to the u, where u is a function of x. So we're going to apply again the Boxton formula, which is e to the 2x times 2, right? The derivative of 2x is 2. Okay, what would you do with something like this one? The derivative of 7 times e to the power of 4 tangent x. Let me give you a moment. And what do we get? So first the constant multiple, the constant remains. You have e to the u, it's going to be e to the u times u prime, right? So it's going to be e to the 4 tangent x times the derivative of the power, which is 4 times secant square of x. And finally, I can combine the constants and bring that secant square up front. So I have 28 secant square of x times e to the 4 tangent of x. Any questions about the solution? It doesn't really matter. No. You can put either one first. But I would suggest that we at least combine the constants to get it to 28. Okay? All right. What about something like this? X times e to the 3x. The derivative of x times e to the 3x. Okay, which rule should I be starting with here? The product rule, right? So based on the product rule, we want the first times the derivative of the second. Okay, the derivative of the second will be 3 times e to the 3x plus, what else will I need? So I have the first times the derivative of the second so far, plus the second multiplied with the derivative of the first, which is 1. I don't even need to bother putting that down there, but I will do it anyway. Now what can I factor out? E to the 3x. And we have 3x plus 1 on the inside. So far we've been looking at base e to a power. But what if you have something like 2 to a power? There's just going to be one extra link there, and you're going to multiply everything by ln 2. Okay, so do it as if you were doing an e to the x problem, but then at the end you also multiply everything by ln 2. That's because, remember, the first, on the top here, I showed you what happens with a different base. You have to multiply it with that ln of the base. Okay, so let's do this one. But first, is there a question, Preston? Yes. Yes, because that I was getting when I was differentiating e to the 3x, and the derivative of e to the 3x is like e to the u times u prime. So it's like e to the 3x times the derivative of 3x. But I happened to put the 3 up front. Okay, that's how I got that one. Any other questions on the previous examples before we try the next one? Okay, 2 to the sine x. Look at this as 2 to the u. So the derivative will be 2 to the u times u prime. However, because the base is not base e, you will also multiply it by ln of 2. It's going to be 2 to the sine x times what? The derivative of sine, which is cosine x. And because the base is not base e, it's not going to be as simple or as natural as we expect it to be. So we'll have this unnatural extra constant showing up, which is ln of 2. So where's the ln 2 coming from again? I'll go back to the top to show you. It's coming from here. Anytime you have a different base other than e, you will always end up with a factor of ln of that base as a result of differentiating it. The only time that base doesn't appear there is if you have base e, and the reason is when you have base e, you have ln e, right? ln e is 1, so it never shows that. We never bother putting that down there. ln e is always 1. To be quite honest with you, 99% of the time, the examples you're going to see are going to have base e. It's just by far used most commonly. But every once in a while, you might have like one example on the homework, maybe like one example on the review sheet, I think, that has a different base. So I just want you to be at least familiar with that other rule as well. I was just going to leave them like that, because there's really not a very good way of combining it. I could put them up front, but that's pretty much all I could do here. Okay, in a minute, I want to show you an explanation. Why is the derivative of e to the x e to the x? So I just told you that as a rule a moment ago. Just give me a minute. I want to look at something. Okay. Before I show you the proof, there's a preliminary work we need to do. I want you to explore this limit for me. What is this limit as h goes to 0? And it looks like it's coming out of the blue, but it's going to be all connected as we're looking at the proof of the derivative of e to the x. If you plug in 0, what do we get? Pedro, would you agree with me that if I plug in 0, I'll have e to the 0, which is 1, minus 1, which is 0. And on the top bottom, I have 0. So do I have 0 over 0? Okay. So what do we do when we have 0 over 0? We say just it's not defined and we leave it at that, or do we do something extra? What was 0 over 0 called, guys? Indeterminate. That means you got to do something more to get rid of the indeterminate form. Sometimes you multiply by a conjugate, sometimes you factor. None of that applies here, right? So what we really need to do here is maybe use a numerical method or a tabular method. So let's do this. Let's go to the calculator. Go to your y equals screen. In parentheses, enter. You know, it's hard to enter an h to the calculator, so I want you to enter x. This to e to the x minus 1. After the x, you have to close your parentheses. Again, close it again for the numerator. And I want you to look at what happens to this limit with your, go to your table. Like enter like x equals 0.0001 or negative 0.001. Approach from both sides. Let's see what happens. So I'm trying to be e to the h minus 1, but I'm just using x because it's easier to put in the calculator. Oops, not 11. Divided by h, in this case again x. I'm going to go to the table. I got 0 over 0 when I tried to do this with a regular limit. That did not work out. What did I do? Let me go back, sorry. Oops, yeah, I have a really hyper pen here. Okay, the second right arrow goes to the end usually. This one is not doing anything. Okay, let's try it again. Okay, thanks for noticing. I was going to wonder, why am I getting these weird results here? Okay, now let's go to table. I'm going to go to table. Okay, for x, approaching from the left-hand side, if we're approaching towards 0, I could put like negative 0.1. I could put negative 0.01, negative 0.001, right? Okay. Approaching from the right-hand side, you know, you're going to need values like 0.1, 0.01, 0.001. So approaching from either direction, from here or from here, where do the y values appear to be approaching? They appear to be approaching 1. Put in exactly 0, you're going to get error. It's not defined as 0, but as you're approaching to 0, the limit exists, and that limit is exactly 1. So that's what we're obtaining from this screen. I'm going to copy that over. Okay, I want you to remember this limit as we're looking at the next item. Okay. Which is going to be the proof of this fact. Yeah, it's so easy, you know, yeah, derivative of e to the x is itself. But how did they come up with that? You know, is there any reason to it? Did they just make it up? Where does it come from? So let's think about that in the next couple of minutes, if we may. If you have no idea what the derivative of a function is, what would you start with? Exactly, I heard x plus h, the definition of derivatives. And the definition of the derivative was limit as h goes to 0. So basically we're going to say, okay, we're going to use the definition of derivatives. So by definition, this is equal to limit as h goes to 0. Okay, what is f of x plus h for this function? Replace every x with x plus h, and what do you get? E to the x plus h minus f of x, which is e to the x, everything divided by, come on guys, you know that's h, right? This is the definition of derivatives, right? Just to remind everybody, it was like f of x plus h minus f of x all over h. Limit as h goes to 0, right? This was the basic definition of the derivative. Okay. If you substitute 0 for h right now, what do you get? E to the x minus e to the x, which is 0, over 0. So we get 0 over 0. We got to do something more here to simplify it. And what I'm going to do is I'm going to factor out e to the x. You see, e to the x plus h, can I write it like this? Can I write e to the x plus h as e to the x times e to the h? Yeah, because if you add the exponents, you get the previous step, right? If the bases are the same. and you're multiplying two expressions, you would add the exponents. That will give you the same thing as we started with. So you can write e to the x plus h as e to the x times e to the h minus e to the x over h, and all we have to do is factor out e to the x. So now you see why we worked on that limit a minute ago. E to the h. What is left from the second term if I factor out an e to the x? 1. Everything divided by h. Now, what do we know about that limit once again? Yeah, we saw that it approaches to 1, right? That limit of e to the h minus 1 over h as h goes to 0, that goes to 1. Okay? Now, what about e to the x as h goes to 0? You see, e to the x is considered to be a constant. There's no h in it, right? The limit is taken as h goes to 0, right? So when you have just a constant, think of it just a constant, no matter where you're going, the limit is going to be whatever that constant is. So it turns out to be just e to the x, because e to the x does not depend on h. It can be considered to be a constant with respect to h. So the answer is e to the x times 1, because we just saw that the limit of the second part was exactly 1. So therefore, we're getting what we were trying to prove, right? Derivative of e to the x is going to be e to the x. So the proof is not that easy, perhaps, but the conclusion is very easy, and that's what we're going to be using in most of the examples, the conclusion of that rule. Okay, so far we've been talking about the exponential function. I also need to show you the derivative of the natural log function, the ln function. And once again, it's really easy. Okay, I have to say it's not as easy as the exponential function. That's by far the easiest one. Derivative is itself, right? How easy can it be? But this one is not too bad either. So the derivative of natural log function is very simple, 1 over x. So if you have ln of x, its derivative will be 1 over x. And in a little bit, if I have time, I also want to show you the explanation for this one. Where did this come from? You know, are people making these things up, or is there real theory to substantiate, to back up these rules? Of course, you know, if they've been publishing them in calculus books, you know that there must be some theory behind it. All right. What if it's u? So u is a function of x. What is the derivative of ln of u? As you might imagine, the chain rule kicks in. Okay, so it turns out to be 1 over u times u prime. And we're going to do a few examples about this one as well. So to differentiate ln x, it's just 1 over x. If you have anything but x, like x squared plus 5, then you have to do 1 over that times the derivative of the inside. Okay, for instance, let's take a look at this one. Let's find the derivative of ln of 3x squared plus 5. So what will be the derivative be based on this rule right here? 1 over u, in this case, 1 over 3x squared plus 5, right? Times the derivative of the inside. And Crystal, would you agree that the derivative of the inside would be 6x? Right? Because we're just differentiating 3x squared plus 5, right? You can leave it like this or put the 6x on the top if you like, same thing. All right, could you try this one for me? Derivative of ln of the square root of 5x plus 7. It looks complicated, right? It looks a lot more difficult than the previous one. But we learned how to simplify logarithmic functions today. How would you simplify this? The square root means which power? A half. By property of logs, can you bring the half down? We should be able to. Now, if you don't do that, this is what you would have to do. If you don't apply the property of logs, you would have to do 1 over that quantity times the derivative of that quantity. It's going to get complicated when you're differentiating its square roots, right? But it's easier if you begin with a simplification. If you say, okay, the given question is the same thing as, I can bring the 1/2 down and write it like this. When I did this, did I take any derivatives whatsoever? Did I do any differentiation? No. All I did was use properties of logs. That's algebra, right? To simplify it. Now I will give you a minute to finish the question. Differentiate this. And when you find the derivative, don't use d over dx anymore. D over dx is saying find derivative of what comes after it. But once you choose the derivative, you don't need to keep the d over dx notation anymore. You have a constant multiple. The constant remains. What is the derivative of ln 5x plus 7? 1 over 5x plus 7 times the derivative of the inside, which is 5. So I can write this like this. 5 over 2 times 5x plus 7 on the bottom. Not too bad, right? If you remember to simplify first, these are going to be so much easier than if you don't simplify them first. Okay, I'll give you another one. I'll come back to that. Okay, let's take a look at this one. The derivative of, let's find the derivative of ln of quantity 7x plus 5 times 2x plus 1 to the third. Okay, after this example, I think we're going to go to the groups just to do some more practice. So this will be our last one right now in class. If you don't simplify it, you have to do 1 over u times u prime. U prime would be a mess, right? You have a product, you have a cube, it would be a huge mess. It's so much better if you simplify it first. How can we simplify it? Okay, first, I'm not taking any derivatives, so I'm going to keep that differentiate command in there. Just let me rewrite this. How can I rewrite this? ln of 7x plus 5, and then what? You have ln a times b. We know that's ln a what? Plus ln b, right? So I should write this as ln a and then plus ln b. But as I'm writing it, you know, the 2x plus 1 to the third, I might as well bring the power down and put it right here. Okay, let me see for a moment if you agree with this simplification. I did not use any differentiation here. Just algebra to simplify it. You know what this reminds me of? Earlier today we did a problem. Which one was it? Near the last, one of the last ones when we were doing our review process. Which one was it? Five A. First you write it out as different logs and then you're going to differentiate it. Okay, look at 5A. Okay, the rest should be easy. What is the derivative of ln 7x plus 5? 1 over 7x plus 5 times 7. And the constant remains for the second part. What is the derivative of ln of 2x plus 1? 1 over 2x plus 1 times what? Times 0 of the inside. So you could just rewrite it if you wish as this. You know, if you check the books and answer, chances are they even go further. They combine them as a single fraction. For my purposes, you don't have to do that. It's okay, you know, to leave the answer as what we have here. All right, for the sake of those viewing this at home, let's go ahead and finish a few more things to conclude the lesson today. And to do the solution for this problem, we're going to begin with the product rule. So we write down the first item times the derivative of ln x, which we learned is 1 over x, plus product rule, we need a plus in the middle. The second item times the derivative of x with respect to x, and that is 1. So when we simplify, we're getting just 1 plus ln x as the answer. Now, as I was going around the class, I was asked, why do we need to use the product rule here? Clearly the answer is because we have two expressions where both of the expressions contain the variable x. If we had like 5 ln x, we don't really need the product rule. We can use the constant multiple rule, meaning leave the constant where it is, differentiate the ln x. But anytime you have product of two expressions, both of which contain the variable, you will need to use the product rule. Okay, we're going to look at a few other things. First of all, an understanding about where did this rule of derivative of ln x equals 1 over x come from. Let's try to take a look at that for the next few moments. So we want to see why is the derivative of ln x 1 over x. Now we already know, of course, that the derivative of e to the x is e to the x. We need to use that in this proof because otherwise you have to start from basics using the definition, and sometimes it's a more complicated approach. So we're going to try to convert ln x and try to write it in the exponential format. If you let y be equal to ln x, how can we rewrite this expression without the ln? Well, you can exponentiate both sides, right? We've looked at it earlier today. You can write this as e to the y equals to x. That's one way to write it. E to the y equals to x. Because remember, the hidden base was e. This is the exponential form of y equals ln x. Now let's differentiate both sides of this equation with respect to x. Starting with the derivative of e to the y. That is kind of like e to the u. And the derivative of e to the u with respect to x is e to the u times u prime. So that's what we will have over here. We will have e to the, let's see. So basically I took the same equation as the step from above, and I'm saying I'm going to differentiate now both sides with respect to x, but I haven't yet taken the derivative. I'm doing it in the next step. So derivative of e to the y with respect to x is e to the y times dy dx, very much like the way we differentiate e to the u, right? E to the u times u prime. And on the right-hand side, derivative of x with respect to x is 1, so that's what we have here. And remember, we were trying to find dy dx, because if y is ln x, we're trying to find what is the derivative of ln x function. So if we could solve in this equation for dy dx, we will be done. That's what we'll do next. Solve for dy dx, and you get 1 over e to the y. Now, it's not common, though, to leave an answer in terms of the y variable. So what we're going to do is we're going to go back and substitute the y back in there. Remember from up here that y is equal to ln x. So go ahead and place that in this equation. Instead of y, go ahead and place your ln x, as we've done over here, e to the ln x. And of course, you can simplify that. E to the ln, it cancels each other, right? They're inverse functions of each other, and voila, we're left with 1 over x, which is what we were trying to prove. So to summarize once again, the derivative of ln x function is 1 over x. And here, we made use of the fact that the derivative of e to the x is e to the x, and we basically rewrote the ln function in terms of exponential functions and made use of what we already knew. Also, as a side note, now that we know the derivative of ln x is 1 over x, what do you do if you have a different base? Something like derivative of log base a of x. How do you answer that question? Of course, ln is base e. What do we do when we have a base a? We will begin by using the change of base formula. Log base a of x can be written as ln x over ln a. That was one of the rules we reviewed earlier. Now, ln a is just a constant with respect to x, so it can be factored outside. So ln a from here can be factored outside over here. So what is the derivative of ln x? That's 1 over x. So the answer becomes 1 over ln a times 1 over x. In other words, if you have a base other than e, you're going to deal with an extra factor, in this case 1 over ln a, and you never have to memorize this. If you know the change of base formula, you can always get it. For example, say we want to find the derivative of log base 3 of x. The answer would be 1 over ln 3 times 1 over x. And if you didn't want to memorize the rule, you could just rewrite it with a change of formula. This is ln x over ln 3. And ln 3 is just a constant that can be taken outside. And you're left with the derivative of ln x then, and that is 1 over x. So that's how we're getting our answer there. Of course, when the base is e, in the case of, like if you had just ln x, here you technically have ln e, and that's 1, so that never shows up in our final answers. So one more example. Again, you first rewrite it in terms of change of base formula with the base of e. Then factor out 1 over ln 5, and then take the derivative of ln x, which is 1 over x. So this is the answer for the derivative of log base 5 of x. Again, most of the time you'll be dealing with the ln function or e to the power, but I just want you to have a little bit of exposure to different bases as well. But I would say 90 to 95, if not 99% of the time, you'll see the examples I have assigned is going to be mostly the exponential function base e. And the reason for that is because all the way through the calculus sequence, that is the base that gets the most use. And finally, this is a little bit different. This is called logarithmic differentiation. This is not derivatives of log functions. It's just the log functions will help us to find the derivative of some mystery function, like in this case, x to the x. How do you differentiate that? You couldn't bring the power down and subtract 1 because that only works when you have like x cubed, where the top is a known number. You couldn't use a rule like this because it only works when the bottom is a given number. Here you have variable on the base and the power. What are we going to do? So this is what we do in a situation like that, with a variable base and a variable power. You start by saying, let y be the given expression, such as x to the x. Then we apply ln to both sides. So ln y equals ln of x to the x. And if you simplify, you will get ln of y equals x times ln x. Now let's differentiate both sides of this equation with respect to x. First, start with derivative of ln y. That's like ln of u. The derivative will be 1 over u times u prime. In this case, 1 over y times dy dx. Equals, on the right-hand side, we have a product. To differentiate that with respect to x, I will have first times the derivative of the second. Derivative of ln x is 1 over x, plus second times derivative of first, which is derivative of x with respect to x is 1. And remember, we're trying to find dy dx here, or y prime. So I need to multiply both sides by y to solve for y prime. And simplifying what's in the brackets, we get this. Just as a final touch, it would help to rewrite what y is in terms of x. That way we can leave our entire answer in terms of x. Okay, that was the last few items that I want to include in this lesson. So that concludes our lesson on derivatives of exponential and logarithmic functions.